Live. Hi. Who knows? Hello, everyone. I have no idea that this works. There's no sort of monitor. So if you can put something in the live chat that suggests that you hear anything I'm saying, that'd be fantastic. How are we all? Are we doing all right? Are we enjoying quarantine? Everyone finished Tiger King. That's basically all I've achieved the last week. Today I want to carry on with what we were doing last week, and I forgot to show the title slide. There we go. So this week we're going to carry on with the code we wrote last time, and we're going to start with, I think, a thing that I did right at the end of the last one and didn't really give the attention it deserved. And so I've called this one writing libraries for people you like, because I think when we talk about timely dependencies, injective type families, all of these things we talk about today, the reason we go through all this effort is so that the end user doesn't have to deal with as much, I guess, work. You know, we try to eliminate as many calls as possible from what the user has to do to use our library. People have said hello. There's some echo. I'm very sorry about. I debated whether I should do this one under table, a duvet over it, but it's really hot day, so I decided not to. I'm very sorry. That's going to be a shame for all of you. But if there's a real problem, and if it sounds like I'm doing this in an opera house, next time I will crawl a table and I'll bring a desk fan or something, and it will be fine. Studying and chopping. Oh, that's no good. Okay. Should we do some live testing of alternatives? If I figure out how this software works, and if I turn this to and then turn this up. It's really hard to hear. Oh no. Okay. In which case, backup plan. What if I just make this 10? Okay, so that didn't look good. Oh no. Is this better? Is this better or worse? Oh man, the lag is really annoying here. I'm going to assume it's better, and then wait, and then if someone says it's terrible again, I can have another plan. This is a shame. So I bought a microphone a while ago, and it turned up this week, and I thought that's a great idea. That'll fix everything. But still, it can't beat the internal mic in this 8-year-old MacBook Air, which is baffling. Yeah, wild. Everyone says it's better. Seems to be improving. Oh wow, that's fantastic. There's actual acceleration to the improvement. That's good. Right. In that case, I will assume everything's fine. I'll assume nothing's gone too wrong, and I'll just get started. So, writing libraries for people you like is the topic of today. Anyone who was here last week will have seen all of this code, at least. We wrote this together. I think it's pretty much exactly as it was. I might have tidied it up a little bit, but I'm pretty sure it's the same code still. We started off with our user type, so just a plain old user. We talked a bit about the motivation about why you might want an HKD, like user F, and why F wrapping all the parameters might be useful, so we can introduce partiality with maybe, or kind of, programs with I/O, or however else we want to do it. And then, because of all the fuss we had with EQ, ord, show, and all that, we said, well, probably the easiest way to manage this complexity is to to have these two functions, construct and destruct, which say I can kind of go in and out of my HKD type as and when I need to, and if I need to do something like print it out, I can kind of stitch it all back together, get the original type and show it, and I can construct my original type from the HKD pieces, and I can destruct a proper type into an HKD. And the thing we talked about right at the end of last time was, now I've kind of written this type family that supposedly says for any type that implements generic, I can programmatically produce the generic rep that its HKD type would have if I wrote it by hand. So I no longer need user F, because if I wrap all the parameters in an F, I get the same thing without having to define that type. And then right at the end, we said, so now if I hide that type family inside this new type, then my beloved users get to, write a type like HKD user maybe, and that's effectively equivalent to user F maybe. It has the same generic rep. The thing we're missing is a way to use that type, because no one wants to write programs that use the generic rep. The generic rep is quite ugly, so it's really good if we can provide an API that feels very familiar to what we had when we manually wrote the HKD type originally, the user F type originally. So the first function we looked at writing was destruct, and we ran into a problem, and because I think I'd left myself 10 minutes, as I'm prone to doing, I didn't really have time to explain what the problem was, how we can avoid it, and why the solution I came up with in those 10 minutes is subpar. So this time I want to start by basically replaying those steps, running into the same problem, and then stopping and explaining what's going on and why GHC is unhappy with us at that particular moment. So if we take these functions, construct and destruct, bring them down here, this is going to be where we'll write our masterpiece. So if we start with destruct, we have this type that says, for any applicative F, I can turn a user into user F parameterized by F. How do I do that? Well, according to the implementation, I take every field, call pure on it, and then put them inside a user F. So again, just as we saw with the type family, there's a very mechanical way of getting from our type into its destructed form, just as there's a very mechanical way of getting from our original type into its HKD form. So the question we want to start asking is, why then does it matter that this is a user? Can it not be that general? Can we not say, actually, destruct says for any applicative, I can turn an X into an HKD XF? And that's the function I want to write first today. And hopefully it kind of, if the type family shows you the pieces of a generic rep, hopefully this shows you how to, actually work with it, manipulate it, and write some value level code that does something useful. So I've got GHCID running, which is good. So as I think we said last time, if you need to write a function that behaves differently depending on the types you give it, one of the most popular ways of doing this is to write a class. I'm going to call it construction because I'm going to come back and add the construct method later. I realize right now it's not a particularly great name for a class whose only method is destruct. And GHCID is happy. So we have an instance of construction if we can implement this destruct function that says for any applicative F, I can lift this X type into its HKD form. And ideally the way we want to do this is with its generic rep, because we know that anything inside an HKD has a generic instance. That's sort of the basis of the library. We want to do as much as possible with the generic rep, and then we don't have to impose extra constraints on our users. I think the library does a good job of actually reducing the boilerplate down to the line deriving generic, and that's kind of the goal. Is I don't want anyone to have to plan any further than that. So typically the way we write these sorts of classes is you'll write one that looks pretty, like this. It looks fairly readable and understandable. And then you'll write a kind of complementing class that works on the generic rep. Typically you prefix this with G for generic, and all it does is basically the same thing, except everywhere we used to write X, we now write rep, because we're dealing with the generic rep rather than the original type. The P there is a phantom type. I think we talked about it briefly last time. I'm not going to worry too much about it. I think for the purposes of this, it is a good enough intuition to say every time you have to express a value that is a generic rep, you just write rep P, and P is a thing we ignore. It's also, in fact, we did go over it last time because it's why this is void. This is the kind of phantom type that's at the end of generic reps. It has a lot to do with, say, deriving functor and things that are of kind type to type rather than kind type, because the GHC generics toolkit kind of shares a lot of code between the two. So I think the original rationale was if we write everything at type to type, then everything that's type just works because we can just have a phantom type. Which, again, if it doesn't make a lot of sense, don't worry too much about it. So we've got this beautiful new generic class, and so typically what we end up doing at this point is we say if X implements generic and rep of X implements G construction, then X implements construction. So we write this, put a G there, generic destruct. Then GHC explodes, it tells us flexible instances, it probably tells us flexible context next. Yes. Turn on some extensions, turn on undecidable instances. Just do what we're told. Good, and it stops complaining. Undecidable instances here is not a thing that is worth worrying about. All it means is that, is it worth going through? Basically, in GHC's kind of simple way of figuring out whether an instance is going to terminate, it says, does the thing on this side of that arrow, is that, quote, bigger in some sense than the thing on this side? So if you think of like EQ for list, instance EQ X is EQ list of X, by GHC's thinking, list of X is a bigger problem than X. So this instance is fine because every time I look at its constraints, I'm taking on a smaller problem. So in theory, at some point, I'm going to terminate. I'm going to hit the end of that recursion. It's not happy here because I have a type family, I have rep, and that means it's not. It can't do that search. It can't tell that the problem's getting smaller. I think the way it actually puts it is X appears more on the left than the right. So in generic X and G construction rep X, but needless to say, we turn it on, and by turning on undecidable instances, what we're saying is, don't worry about it, GHC, I will make sure that this terminates, and if it doesn't, you know, on my head be it. So the instance of destruct, according to GHC ID, must take an X to an HKD X of F. The way it's going to do that is it's going to take that X, it's going to go from that X to a generic rep, then it's going to destruct it generically, and then once we've destructed it, we have the rep, so we can wrap it back up in its HKD wrapper. This is completely wrong, sorry. This should be GHKD if I rep P that, right? Are we happy with that? We're not happy with that. No P. Good, good. There we go. What about making default destruct equals to destruct? Oh, that's a good question. So you could do that. You could do that. The reason I haven't is because if I do that, every type like user, I have to say deriving construction. I don't want to do that. I just want to write deriving generic. If I have a default destruct implementation, then I have to say user is a thing that implements construction, which isn't a thing I want to do. I just want to say anything implements construction, and once you go looking, I want you then to check that that thing happens to be generic and happens to satisfy G construction. So yes, it's a perfectly sensible strategy. It just adds extra boilerplate, which in this case means one extra word, which is infinity% more boilerplate that I'm happy to introduce. So, but thank you. Good question. So we now have this. We now have this line here, but we've got a friendly new problem that looks absolutely horrifying. And so what I did last time, last week, is basically I did what it said, which is turn on allow ambiguous types and start adding type applications frantically everywhere to get the thing done. And what I want to do today is figure out why shouldn't user just derive generic given the constraints of GDIST. I will come back to this later because I'm not sure I understand. So looking at this, the problem it is having, according to this error, is that it can't match type GHKDFI rep F0 with GHKDFI rep F, which is a really odd and scary looking error. But let's try and break it down and talk a bit about how GHC infers types. So if I look at this line here, this destruct signature, what you can see is that there's this x, and that's fine. X is an argument to the class. There's also this f parameter, and you'll notice that GHC, in fact, if I delete that and that, GHC doesn't complain that that's ambiguous. GHC says everything's fine. The reason it does that is because at some point I will merrily, my code, I will use destruct, my thing, and GHC can infer a type for that, my type, maybe, or whatever. At that point, it can look at the two arguments to HKD, which are my type and maybe, and it can say, right, X must be my type and F must be maybe, right? It can unify those two, and so it can figure out F as long as it knows the type of the result. So once it gets the HKDXF, it can kind of it can work backwards and figure out what the F this signature is talking about based on the type of that result value. So in general, there's a kind of approach that GHC takes to be able to do this, which is to say, if I have a value of type HKD XF, and I want to make sure, does this, I want to unify this type with HKDYG, GHC is able to say, yes, it does if X is Y and F is G. So another way of looking at that, and maybe a slightly simpler example, is to say, what happens if I have to unify maybe A with maybe string? So in this instance, we are smart enough to say, oh, A is string, right? We can figure out that variable in our heads, and sure enough, GHC is clever enough to do that. And the reason it is clever enough to do that is it uses a principle, a kind of rule for unifying types, which we call matchability. So what it says is, in general, if I have to match something of type FA with something of type GB, or rather, if I know that FA equals GB, I also know that F equals G and A equals B. So if I know maybe A equals maybe string, I know maybe equals maybe, and A equals string. But similarly, if I know maybe A equals F string, I know F must equal maybe, and A must equal string. So I've got this neat trick for saying, you know, if I need to figure out an equality between these two FA and GB, I can kind of split the problem into two pieces. And sure enough, this works fine. You know, if I have to do IO of A or anything else, everything's still very happy. And we call this well, the general rule that FA is GB implies F is G and A is B. We call this matchability. This is actually a kind of composite of two simpler rules, which is if FA equals GB, from that, if we can tell that F is G, we call that generativity. And if from that we can infer that A is B, we call that injectivity. So all of these are rules that, or rather matchability is a rule that GHC uses to figure out types. So although this F appears here, that's fine because we'll get back, we'll use this function and we'll get back something of type HKD user IO. And based on this rule, GHC can figure out that, oh, the F must be IO, right? I can deconstruct the type and everything's fine. So that's great. But there's a fun feature in GHC that breaks this idea, and it's type families. So if I write a type family that takes a type and says whatever it is, it's unit, right? Now I want GHC, I want to give it a constraint, like, sorry, let's change this. Let's make it IO unit. I want to say rect int is IO unit. If GHC applies that matchability principle, what you learn is that rect equals IO and int equals unit. This is obviously not true and not good. This is false, right? We shouldn't make that kind of deduction given an equality between rect int and IO unit. It's not possible to apply this matchability rule, which is interesting. And there is some work coming any day now, I'm sure. Chonga, I know you're listening. If that appears in the compiler, I'd be very grateful. To say there are kind of, at the moment, this distinction is a bit cloudy in GHC, and it should be possible to distinguish between something that isn't matchable. And if I can do that, then I can get rid of restrictions like a type synonym not having all its arguments, or a curried type family and things like that. If I have a way of knowing the difference between something that is matchable and isn't matchable, you know, I can have a bit more flexibility. Today, however, we are stuck. So let's return to the error we actually got, which should just appear. Yes. So GHC has exploded. Panic. Couldn't match GHKDFI rep F with GHKDFI rep F. What's maybe more interesting about this error is this line, which says GHKD is GHKDFI is a non-injective type family. Now if we remember, the injectivity rule would be FA equals GB implies A equals B. If that were true, if that rule were in play, then we would have GHK deify rep F0 equals GHK deify rep F implies F0 is F, and it would be able to solve this. There wouldn't be an ambiguity anymore, right? The problem right now is in this gdestruct method, the only place you see F is as a parameter to a type family. And if you think about the shape of this, F would be your type family and A would be your parameter. So the problem is that, at least in its current form, GHC can't take the answer to GHK deify rep F and work backwards to figure out what the inputs were. And because it can't do that, it's now complaining and it's saying, you know, I have no way of unifying the parameters. It's an ambiguous type. I can move this ambiguity check to the call sites, and then you can use type applications and everything else. But the interesting part of this error for me is that having a note that says non-injective type family implies that there is such a thing as an injective type family. And based on these notes, that would be the thing we want, right? That would solve our problem. Hello, Sandy. That's weird. I haven't spoken to you in ages. Fantastic. So the question then becomes, how do we write an injective type family? How do we write a type family that in this case says, based on your output, I can tell you your inputs? So there's a language extension, as there always is. It's not type families, it's type family dependencies. I think it's probably so named because it's like functional dependencies for type families, which means it's an incredible name. It absolutely does what it says on the tin. And what we're going to say here is that instead of this line here that says I am a function from rep and f that results in some rep, some type to type, I'm going to say rep and f result in a value, I'll call it output, but output determines rep and f, which is to say, if I know the output, I know rep and f. And now what I'm asking GHC to do is say, basically I want you to, in a sense, write me the opposite function. Like, write me a function from the outputs to the inputs. And if you can convince yourself that that's possible, we'll have a lovely time. The requirement is that the right-hand side always uniquely determines the left-hand side arguments. So it's kind of the same mechanism as functional dependencies in that regard. However, as you can see, GHC has got upset because there's an equation or a pattern match in our type family that violates this injectivity annotation, this functional dependency. And it's even kind enough to point us to the problem cases, and they are these two. The problem, if you think about what we said, we want to be able to figure out what the inputs were from the output. The problem is that if I have U1 as an output, I know rep is U1, but I have no idea what the F was. Because if I GHK deify U1 according to maybe or IO, I get the same result. So I can't work backwards from U1 to figure out what rep and F were. And the same is true of V1. So just as a kind of sense check, if you say you can only figure out the rep from the output, that's true. We can't tell anything about the F, but we can tell what the rep was. And now it's fine, but of course we haven't solved our original problem, which is figuring out what the F was. So in the library, I do what probably isn't the best solution to this problem, but certainly works. And that is just delete the two problem cases, and everything's fine. Yeah, again, there might be better ways, but the rationale was, how many times do you want an HKD version of a type with no constructors or a type with no parameters? I would argue, actually, given the state the library's in now, you probably don't need sums either, because most of the functions don't operate over sums anyway. But we can leave that in for now. Which means last time when we talked about the 6 cases you have to deal with when you're writing anything to do with generic reps, we've now shrunk that down to a set of 4 things. So we've made our lives 33% easier, which is great. But more importantly, we've introduced this dependency here. And in terms of our intuition, I think this dependency makes sense, right? So if I know the HKD version of a type, I should be able to figure out what the original type was and the f. Because the f is the thing that's wrapped around every parameter, and the original type is the thing without all the f's in it. So it does feel like they are things we should be able to work out. And of course, GHC rightly said, that's true unless your type has no arguments, because then it has no f's in it, or it has no constructors, because if it has no constructors, it also has no arguments with no f's in them. So we've taken away our kind of, potential problem rules, and now everything's happy. Now we have inference on our side. And so this line is perfectly fine, because it knows when I get a result of type GHKDFI rep FP, based on that assertion, based on that injectivity annotation, I know I can infer what f was. So f's no longer ambiguous. You don't need to tell me what f is. I'll figure it out based on context. And that's great, because now, firstly, we don't need to turn on allow ambiguous types. We don't need to ask our users to add type applications to tell us which f they're dealing with. We can infer it all from context. So for what I would argue is a very minor loss in functionality, like some very edge cases, we've made the library a much easier API for our users to get involved with. So with that in place, now our class is fine and there aren't any ambiguous variables. We can start writing instances. Typically, when I do this, what I tend to do is I write an example, which in this case we could say is that, and I'll say destruct user Tom 26 true, just so it gives me an error, right? Just so it gives me an error that says this is the generic rep that you haven't written an instance for yet. Because then what I can do is I can kind of, just as we did with the type family above, we can kind of work through the layers of the tree down to the leaves. So the first step is this D1, and we talked about this a bit last time. D1, C1, and S1 are all kinds of metadata, just different types of metadata, which in GHC Generic's wonderful naming scheme is called M1. It has an index, so D1 is actually M1D, C1 is M1C, etc. And that wraps around some internal information. So you have data type level metadata around constructor level metadata, around the product of the selector level metadata. So if I write that, I get a smaller error, right? It said, okay, well the top layer was D1. I now have an instance that matches that, as long as you have an instance for the thing inside, which was a C1, and it says, well that's also an M1, so I have an instance for that, as long as you can match the thing inside. And we've now hit the product level, so over here, this thing here. It being infix makes this error a little harder to read than it should be, but this is the kind of, the next operator we have to deal with in the tree. As you might imagine, just as we did in the type family, if you can deconstruct the left and you can deconstruct the right, you can deconstruct a product of left and right. And now the error gets really small, because we've said how we're going to deconstruct the product. The only thing left is the actual leaves, and that doesn't recurse any further, so we can just say that, for example. So we've written all the classes, and now we just need to implement what these functions actually do. Ooh, comments. I have to leave for a moment. My question was only if the additional strategy you have to instance. Yeah, interesting. Armando, I'll message you because I'd be interested to play with that. I think it would add some extra code, but I'll check before I just say so. Evan, there's a library called Harg, Harg, where my old colleague Alex kind of messed around with the idea of using HKD as a basis for a kind of opt-parse library. I don't know how far he got with it because I left the job, but I would imagine he's probably got a better idea of that question and probably got a better answer for you. Harg, it's a fascinating idea. Cool. So let's write some instances. So destruct for the metadata level. Please don't explode. Haha. Okay, I wrote this in my notes. So GHC, as far as I know, is not going to terminate. It's going to get very upset. And this is a point where I have to run a few scripts that you can tell I've run a couple times. So we're going to write this by hand and not worry about GHC problems right now. But in general, we are going to, according to this signature at least, let's just put it down there. We are going to get a rep, which is going to be an M1 of something, and we need to return the GHK-deified form of that rep. Now, according to our type family up here, the HK-deified form of M1 is also an M1. You don't touch any of the metadata, you just kind of recurse into it. So this function ends up being, very underwhelmingly, M1 of G destruct X. And then hopefully if we turn GHCI back on, indeed, no more non-terminating bugs, errors? Who knows? It might well be my fault. I've not really looked into it. So that's fine. So we've said when I need to destruct a rep, leave the M1s alone. The M1s are not important to this process of destructing the type. So the next layer down, I've got products. So I have a left and a right, and I guess, as may be predictable if you saw the last feed and you've kind of been following the idea here, is I'm just going to end up calling gdestruct left and putting it back together with gdestruct right, because again, that's exactly what my type family says will happen. Products are left, we just recurse down both sides. And sure enough, still happy. And finally, we come to the K1 instance, which is K1 of X. And this says we need to return a K1 of Fx. And maybe we can even get GHC to tell us valid whole fits. Look, there it is. Valid whole fits include pure. So let's just stick that in there. And now we've written the function. So I guess if you've not done loads of generics, this probably doesn't look a lot like a function in the sense we're used to, but I promise that's what this is at least pretending to be. So all we've done at this point is recursed through the rep just as we did with the GHK deified type family up here. So leave metadata alone, go down each side of the product. I haven't done the sum, but you know, exercise to the reader. And then wrap the X in this F value, which we do using pure. So we've followed the shape of the type family, and we now have implemented the destruct function, which is great. So now we know this works, at least in theory, because example compiles, it type checks. So there must be at least enough well-typed code that this example can compile into something, is the idea. We can write a test for this in a second. The easiest way to write a test for this is to go back the other way. And then we can just say destructing and constructing should do nothing to the type. It should satisfy this sort of round trip property. So let's do it. So if we go down to our construction class, we can now live up to the name by saying construct is a function that says, given an HKD x of f, so given a user f of maybe, I can produce an f of x. So I can produce a maybe of a user. And of course, then it says, well, you've got an instance of this class and it doesn't have a construct method, which means we probably need a generic version of it. So we come back up here. We can apply the same rule that what we're going to be going from is this ugly rep here to an f of the original clean rep. And now we get more errors because not only have we not implemented construct, we've not implemented gconstruct in most places. But that's okay, because construct is a function that takes an HKD, if you like, and then generically constructs from that HKD, and finally converts the rep back into the original type. I'm f-mapping because it's wrapped in this applicative f, and similarly up here, I'm gonna end up in some applicative f. So I have an f of a rep, I need to get to an f of the x, so I f-map the to function which goes from a rep to the original type. And with any luck, GHC is happy, at least so far, for a change, which is good. The next problem is that we haven't implemented gconstruct for any of these functions. This process should be pretty straightforward, one hopes. So gconstruct is going to take an m1 of an x, because remember, the GHK-deified version of an m1 is also an m1. It's going to recurse down, construct the x, and then because it's wrapped in that f, we're going to f-map the m1 back over it. So once we've constructed the inner rep, we're going to wrap it back up in metadata. Still good. Perfect. Similarly, gconstruct of a left and a right is going to involve constructing the left and constructing the right. Give me an error. Yes, good. They're wrapped in f, so we can do that. And sure enough, valid whole fits include the product operator. So again, it's kind of the same thing as destruct, but now there's just this applicative involved, at least until we get down to the one interesting instance, which is the k1. And when we get to k1 of x, we have to remember that x here is, if we look over here, is wrapped in this f. So we want to do this basically. How do we get from fx to f of k1x? It's probably going to involve some f mapping, and again, valid whole fits. Just try k1. So GHC can write most of this code, which should annoy you. If it can write the code, why do I have to do it? Should be the question. But that's an argument for another day. So we've now written a function that can take, in fact we can go and look at the signatures, that can take an HKD of some type and reconstruct the original type, and we've written a function that can take an original type and destruct it into an HKD. If everything works, it should therefore be true. We set this to bool, do let input equal that. It should be true that constructing a destructed input is equal to just the input, right? Because round tripping should be satisfied, The just here means that because of all the stuff we did with the injective type families, it can now infer from the presence of that just that f is maybe. So again, I'm getting rid of these annotations, which is lovely because the library now just behaves the way I'd expect it to. But in any case, we can now ask GHCID, is this true? And indeed, look, a passing test, just like that. Magic. So what I think is interesting about this is, let's say I come along and I decide that now my users are 3 tuples. Because a 3 tuple also has a generic rep, this test also passes without changing any code. So we really have written construct and destruct for any generic implementing type, at least any one that is a product type that, you know, kind of looks the way we'd imagine an HKD to look. It has a constructor with a series of types within it. Obviously, because we deleted the U1 and V1 cases, this no longer works for a unital type. Again, I would argue that's fine, but something to watch out for. So we've done it, right? We've written a function that respects the generic rep and can swap back and forth between our HKD version and our original version. So I think if you're sort of following this along to get a better idea about how to write operations on generic programs, what's really interesting is to write an EQ instance for HKD, the HKD type as written wherever. Oops. There you are. This thing down here. So it's an interesting puzzle, just because again it's another case where you have to walk down the tree and you have to. There are, you know, probably some constraints you have to place on the leaves, for example. EQ is a good candidate for a constraint involved in the EQ instance, but also something like semigroup or monoid, right? Because any product type is isomorphic to some n tuple. That n tuple has a semigroup and a monoid instance. It's just either, you know, pointwise mapend or just a tuple full of mempties. So it should be the case that anything HKDable, at least, you know, if we ignore the sum constructors, anything HKDable has a monoid instance and a semigroup instance. So if you're looking for kind of, I guess, exercises for the reader, that would be a good place to go next. And I don't think it's too hairy. I think probably by the time you've done EQ, ORD, semigroup, monoid, you'll probably be so bored of this pattern that it's not worth doing anymore. It really is, I guess, the big reveal with generic programming is you only ever have to write something to deal with the 6 cases. And sometimes one of those cases might be a bit complicated, but there really are only, you know, 6 things of interest. And actually 4 if you decide to delete unit types and void types, which I would thoroughly recommend. So that kind of, I guess, concludes construct, destruct. I wasn't going to implement functions like labels or any of the Barbies API, because I think based on this demonstration, all of that follows pretty much the same pattern. So the thing I wanted to do next was kind of look at how we would get values in and out, namely using some sort of generic lens-like construction. I've been trying to keep these to an hour. If I do this, it's probably going to become an hour and a half. So I guess I throw it open to the comment section. Are you happy with another half hour, or do we pause it here and do part 3 another day? I guess while I wait, if you look at the actual library, the dirty trick is the library uses the generic lens, the generic lens library, to implement this function. It's just a kind of specialized version of the generic lens field function. Doing it that way introduces a different problem, which is in order to use generic lens, your type needs a generic instance, which means you have to write a generic instance for HKD, which it turns out introduces a couple of, I guess, awkward constraints. It's not as pretty, shall we say. Basically, the problem is you have the void there, and you have to kind of map over that phantom type, and to map over that phantom type, you need a functor and a contravariant instance, and this is true for all reps, but GHC can't assert that, so you have to add these functor and contravariant constraints everywhere, and it gets uglier than I would like. So I think the library does it that way, but I thought it might be more fun to kind of, imagine generic lens didn't exist. How would we implement that sort of functionality, a way to get and set values from inside an HKD using the kind of generic lens style. I don't know how familiar people are, but for example, I could get maybe string by saying my user field name. So because name is a field of the user type, I can address it by name, and because in the generic rep I can look up that name and I can see what the type is underneath it, I can infer the correct type for that, I can tell you it's going to be a string ahead of time, and I can also set and modify and whatever else. Cool. Everyone's gone quiet, which I presume means either everyone's gone to sleep, or this is a good place to end, and maybe this was a lot very quickly. In which case, I guess, and I'll probably ask on Twitter or something. I guess the outstanding question is, given that we've kind of gone through the whole of the core of Higgledy, this is basically it. It's the same trick, the same generic kind of functions written again and again, but with different specializations to do different things. So if you look up the instances for EQ Wardenshire, you'll find the same pattern. If you look up some of the Barbies functions, like bprod and things like the constraints B, I think it's called, you'll find the same pattern again and again. So I guess I'll ask, but the question is really, do we want to have another session on generic lens and maybe how we implement that, or do we say we're done with Higgledy, and in which case the next one will probably be about a different library. I released something recently. It's a library called Homes, and it's where I've kind of collated all the notes I have about a type of constraint solving approach called propagation and propagators. I couldn't really find a good resource for it, so I started hacking around with the idea, and then it slowly kind of morphed into this library. And a few people have asked about how it works, so I thought this might be a nice format to kind of, start from scratch and say, how do we build a propagator network to solve some things like, I don't know, Sudoku is the usual example, but, some sort of like small contained problem. Cool. In which case, I'm probably going to finish there, because that keeps me under the hour, and that makes me feel like I've succeeded. Thank you everyone for watching. I will answer comments because I find it hard to paralyze. So I will send messages and whatever. I hope this was useful. If it was confusing, please send me a tweet or whatever, and I can try and fill in some blanks. Probably make the library documentation a bit better. But otherwise, have lovely evenings or afternoons or whatever it is where you are. Stay safe, stay quarantined, wash your hands, etc., etc. And